Pleasure to have Professor Shankar Prasad as a speaker of the colloquium today. Uh, so he's from Jawaharlal Nehru University, New Delhi. Let me give a brief introduction of Professor Das. Professor Das did his MSc at the Calcutta University in 1980. Uh, Obtained his PhD from the University of Chicago, Illinois, the USA. And he did his postdoctoral work at the University of Florida and the Institute of Theoretical Physics, Utrecht, the Netherlands, in the period of 1986 to 91. Then he was visiting scientist at the Bhabha Atomic Research Center from 91 to 92, and then he joined as a reader of physics at the Savant Institute of Nuclear Physics, 1993. Finally, Professor Das joined JNU as an assistant professor in 1993, and since then he has been there. Presently, he is a professor at the School of Physical Science. He is recipient of various awards and recognitions, such as he is a fellow of all three science academies, and also recipient of JC Board National Fellowship, DST, India. So he has been working in the broad area of practical physics and fundamental physics, especially time-dependent properties of many particle systems such as liquids, gas, superfluid liquids, especially, and gases. He's an excellent teacher. He actually taught us, I mean, myself and probably many of us in that generation in several schools, practically schools. So today he would talk about complexity and entropy crisis in the amorphous glassy state. So,
thank you. We First of all, thank you for the introduction. I mean, I've been here many times. At some point, I actually worked here. That was not in this building for 3 months or so. No, it was 6 months. I mean, this was time when CK was here. So the title of the talk is this. Now, the word complexity that I use here is not just a qualitative term that I'm using here. I should say at the beginning. It has a meaning in the context of glass physics. That is the sort of final point that I discuss some of the recent work. But because he wanted to make it a general talk, I'll spend the first part of the talk generally reviewing the ideas that have been used over the years. It's not just this year or that year. Because glass is a very old problem, glass physics. And I got involved in it when I was in my PhD days. And then worked on various aspects of it. There are reviews written. Recently, I'm not that much working on it, except this current work that I'll discuss towards the end. So it will be more a review, and then I'll come to the final thing. This work that I will discuss towards the end, not the whole thing, is in collaboration with these two persons. Of course, the one above me is my teacher, and one sort of little below me is Prakash, who just finished his thesis in my group. And this is the one that I sort of did with Jean more recently. This is not my PhD work. And this is a new way of looking at what we know as mode coupling theories and all that. That's a completely different thing than the work that we discussed. So I'll basically focus the talk on two different approaches to the glass problem. And then the first type, of course, is more well known for microscopic models, glass mode coupling theory and all this. The second part is less known to wider audience. So that's a little different thing. That is more connected to density functional kind of models that Ramakrishnan and all these people have started for crystallization. This is for glassy systems. And also use of replica methods that started for instance. So just to move on, just a very basic point, that is, we know that the solid state is like a regular ordered structure of the individual particles. And I will consider the microscopic level means some individual particles with hard sphere, some simple interaction and all that. And then the liquid is more cohesive, whereas the gas is less cohesive. There is no long range order in the liquid or the gas phase. Now, this theoretical model that we follow for condensed matter systems generally depend on, this is a general problem of glass physics, and that is, because of mobile, it's some noise. Okay, so for a low density gas, there is the inverse Symmetry problem.
Can you move him here? Stand here?
This thing.
No. You just
For the ice stand.
try now.
Yeah. So for a low density gas, what happens is there's the inverse Symmetry path, right? The Symmetry path is large. So you can use the inverse Symmetry path as a small parameter. You need a small parameter to construct a regular model. Whereas for crystal, what we do generally is, that we take vibration around the lattice structure. So you take vibrations around the structure and then expand the theory in terms of the displacement. For liquids, especially very high density liquids, there is no such structure to fall back, or there is no large Symmetry path that you can take the inverse as a small parameter. That's what makes the problem more complicated. So this is a general problem. Now, so this is, I just said that it's more strongly correlated. It is actually a non-local, non-linear kind of problem. So here is just a little discussion for general, yes, that when you have the liquid state and then you increase the density at around 0.496 fatty, that is 50% of the system fat, you start seeing a FCC structure. But remember, this FCC structure is not the FCC structure is actually not the closed pack structure. Generally, if you have some spheres, the closed pack structure will know the FCC structure, but the distance between the particles that you see in the closed pack structure when the packing is about 75% is much higher than what you see in the crystallization. So it is going into this kind of ordered phase even when the structure is much loose. So the entropy plays a very important role in this kind of crystallization. This is of course crystallization transition.
So you said that non-local. I mean, in what sense it is non-local?
We will come to that. There are many general comment. And just to give you a feeling the kind of system we consider, we take simple system, also Hamiltonian systems. These are not like active matter, that the passive systems. So although there are talks of active matter or glass transition in those, I'm not going to be here. But so I will be talking about mainly Hamiltonian systems, and they're interacting with some two-body potential, typical condensed matter systems. And the interaction is given sometimes simpler most of the time. Leonard Jones or Hartz. And the reason you use this sort of model is that the structure is much simpler to obtain from microscopic. One can use other structures, but that's not the key problem of the of this kind of studies. One can use other potentials also. So at the very microscopic level, these are particles which are interacting with the Hamiltonian situation. There is another kind of dynamics that is followed, which is called the Brownian dynamics. That is, you have a big particle and the smaller particles are hitting at random. Now, in that case, the equation of motion for the individual particles changes into a kind of a Langevin equation. That you have a regular part, and then you have a noise, and then friction. So, the key difference between this kind of dynamics that is studied in the liquid is that you see that the microscopic dynamics is reversible. That is, you have fluids which are interacting through potentials which the equations of motion are exactly reversible. On the other hand, when you consider the Brownian motion, the dynamics is intrinsically irreversible. That is, you have a frictional part and noise. So,
There should be another terminal.
Open one. Let me see. Let me check.
okay. So, so these are the two basic kind of dynamics that is considered in this kind of model. That either you have the microscopic dynamics Brownian or the microscopic dynamics Newtonian. These are kind of similar for. Now, the another thing I should say at the beginning that these are quite involved areas, and I will tackle a lot of things. So I will not be able to make a complete justice to everything that I say. So people are more interested in it. I just mentioned. So when you look at the thermodynamics of this kind of system, what happens is it's like the typical, the free energy right in terms of the partition function, and then you want to calculate the partition function and bring the free energy. Now, to conclude on the
মাইকটা খুব ডিস্টার্ব হচ্ছে।
ভলিউমটা কমিয়ে দিন।
So basically, the idea of all this thing in the one kind of calculation I discussed, that is the minimization of the free energy. This is how you calculate the free energy. So these are systems where you have to use special techniques to calculate the partition function and then of course if you know this, then you can conclude on the different phase depending on the minimum of the free energy. How the what are the different phases. Now density in all this sort of explain very important. So what I mean by density is not the average density that you have in uniform state, but think of a density non-uniform, which is a function of position and time. So that if you integrate this function over a little volume, you get the number of particles in that volume. If you integrate it over the whole system, then you get the total number of particles. Now, generally, the kind of theories that we do, we treat this function as a function which is known in space and time. Naturally, if you have particles, then you would not have a situation like that, right? Because if you think of the particle nature of the fluid, then thinking of density, you can think of it in some particle. Let's say you have a volume, and then particles are entering and leaving that volume. Then it can only change by integer amount. But of course, these are treated as continuous functions. So there is a force graining involved in this kind of theories. That is, you average those fluctuations over certain distance in which you can treat the density as a continuous variable, density or momentum. So all the theories that we deal with, these are dealing with continuum field theoretic models. So you have to then understand it as that there is some minimum scale over which you have already post-grained the theory. So that's another key point of this kind of models. And then this is just the simplest sort of definition or whatever you call it. The key thing that is focused on is the correlation functions. So there are two kind of correlation functions that really come into picture. One is the density fluctuation. Then you take the Fourier transform because in Fourier space these things are easier to deal with. And also experimental comparison. Yes. So one thing is that you take fluctuations of the density at two times at the same time. So these are called equal time correlation, static correlation, and then there are dynamic correlation with your time. Now, if this averaging is done over an equilibrium ensemble, then of course this will depend only on the function of time. And the theories that I have discussed here, they are generally done so far for the equilibrium states. So one can raise the issue that where classes are not equilibrium state. I should say that all of the mode coupling theories and all the other theories that I have known, most of them are, except the simulations, are done with the equilibrium approach. Take the system in at least close to equilibrium, metastable state. So that's a limitation of the theory, you can say. But non-equilibrium states are really difficult. So let me just, so that was a kind of a brief introduction to this sort of subject. Now the theoretical models that generally people work with. One is this thermodynamic approach, where this is for the density. Now this density function theory is not the DFT, that electronic density function. Okay. This is something that started in Ramakrishna in proof back 7, where this is what it's called classical density. The density again is a smooth function of space, but and this is static theory. So you have the density treated as an order parameter in the theory, and then what he did in those days, he formed a theory for the freezing condition. That is this thing I was telling you about the liquid to FC system. That his theory was on that, but this has given rise to a general method of studying condensed matter system, phase conditions, and the idea is that there is a mass localization when you are crystallizing. So that instead of getting the density as a uniform function independent of R, you get it as an inhomogeneous function. And whereas TBR and all those people looked at in those days crystallization condition, and that became an industry. Many people on that. These sort of ideas were used for metastatic glassy states also. So these glassy states are intermediate. That means the free energy in those states are intermediate between the uniform liquid state and the crystalline state. So then, let me just very briefly in one transparency. So basically, the idea is to use some kind of a parameterization for the density. So you define it in terms of sums over Gaussian functions, and these Gaussian functions are centered on the lattice sides. So if it is a crystalline state, these peaks are very high. That means the width of the Gaussian, the inverse width, is very large. That means this width of these functions are 1 over alpha. So depending on this parameter alpha, you go to a liquid state or a crystalline state. This was a simple way of studying the density of the crystalline state. And I should say here also, well, TBR actually didn't do it in this term. He did an expansion in the reciprocal space and all that. This formulation was, I think, in they first started this. Then this is actually when TBR says series person. But this is more physical. Actually, more physical picture that is done this way. So these lattice sites are Ri and Rv, you can see. at the different. So when you are studying the crystalline state, you have to give two inputs, and the other is the width. And what in the crystalline transition they did is they showed that beyond a certain point, this lattice is disordered and completely, you have alpha going to zero means completely uniform liquid state. Those states are more stable, whereas at very high density, the high alpha states are more stable, and in crystallization, they showed that for each structure, this is more stable. Now, these sort of ideas were then applied around 1984, actually.
The alpha is the same for all the sites.
That's the simplest approximation. Then many Chandra, Nadia, and those people have done, with variation alpha. But those are again computer models. This is so. So this is what I just had to show you that if crystalline structure, then it is like this, and then if it is inhomogeneous structure, then these widths become very large. That is, all of them contribute the same, and you get the liquid state. These sort of ideas were used for metastable states, and I can't go into all that here. This is not the main focus of this discussion. So the point is that the non-ergodic state is assumed. That means by non-ergodic state, particles are localized. They're moving around, oscillating around some mean position. But instead of a regular structure, a disordered structure. If you are interested on this sort of things, they said this first work on this was just one thing. Others. It's here in 1984. Then Chandra did some work, similar work. Then I did. So these are a way of looking at this kind of amorphous minima of a liquid state or a disordered state. Now, one can even question are these glassy states. It's not shown so clearly, but at least one can say that there are intermediate metastable states for the Ramakrishna Yusuf Hamiltonian in these systems. Now, the other method that we have done a lot of things people have done. These are these mode coupling models and all that, where you have a dynamical model. So you have a dynamical model in terms of a set of corrective densities, which I call phi xt. These are determined by the symmetries and the conservation laws of the system. So if you have a fluid, then you have conservation laws like density, momentum, and all that. So you write down equations for this kind of collective modes, the density, the momentum. I'm not writing the energy and all that. And you, again, the definition of the density means that if you integrate this function over some volume, then it is the mass. Here I'm calling it mass density. You can call it number density also. This is the momentum of the volume. And then one can write down exact balance equations for those things. And this is irrespective of glass. It's for fluids, this sort of theories were done. Hydrodynamics of fluids. So one writes down these conservation laws in terms of exact equation, and one can obtain exact. So these are exact representations of this Hamilton's dynamics that I said. So these are microscopic equations. Now you can average these over some kind of local equilibrium ensemble to get the equations of hydrodynamics. And again, as I said, all these are huge formal areas. You can't go into all that. But basically, this gives rise to a formulation of fluctuating hydrodynamics, where you consider nonlinear coupling of this kind of modes. And this is where the name comes from, is the mode couplings and all that. So, the system is now described in terms of continuum fields and their time evolution to partial differential equations with noise. So now you have nonlinear partial differential equations which you have to deal with to see what are the effects of the nonlinearities in those equations. And this is why I said it's nonlinear. That's the answer. And the reason it is called non-local, this also involves integration over space, because it's a partial differential equation, so you will have integration over space and time both. So you get effects over time and over space through this sort of model, the density. But there's a formal structure of this thing which is quite involved. You sort of take those equations. These are written along the line that Paul Martin and others, Martin Carnot, Martin. These are the classic papers of this developments in statistical physics. So one writes down those equations for this, and the simplest form of this equation is this, which we a lot of times see even in BSc level books, that you have the continuity equation, and then at the linear level it is the momentum density equation, and if you solve this, you will get the two sound modes, the propagating sound mode, which is the normal liquid state. One can write down this kind of equation, and this is what Martin and others initially showed for systems with which are not fluids, which are broken symmetry in them. So you bring no new modes in addition to this, which are called Nambu-Goldstone modes, and write the equations for those, and then form the theory. And this kind of theories were done for liquid crystals and things like that. I think Sriram did a lot of this in his thesis, Sriram Ramaswamy, with Kinetic. And that's a general area of studying systems with less symmetry in fluids. This, of course, was used for glass, and this I did when I was in my PhD, doing my PhD, and it gives rise to this kind of models of fluids which are used in glass transition. Now, what does it mean? I again would not go into the real details of MCT, but
We were considering this set of fields psi xt, which are conserved. So they are also coupled, right? So
Yes.
J of I1.
let me
also
go on.
contains-
I'll show you how they are coupled. The basic method of the theory would be calculation of correlation functions, and then once you calculate the correlation function, it involves diagrammatic methods to calculate nonlinear effects. There one uses the multi-type theories, all that, and then you look at normalized transport coefficients due to the nonlinearities. This simply gives rise to the MCQ. This is as much I have said. Then I'll show you the equation. I'll answer.
I think there is no non-local equivalence to display.
There is no local. I'll show you. Just let me. So when I write down those equations, I'll answer. So basically, these things that I was telling you so far, the developments of the fluid dynamics equation and all that, you can use that to study fluids, and people are using it to study fluids. I have written in last few years papers on active matter fluids, this sort of models, fluctuating hydrodynamics. There's a classic paper of Toner and Tu, where they used hydrodynamic equations, similar equations. We showed that how those equations can be obtained from statistical mechanics, but they are not specific to glass. Where it becomes specific to glass is that you consider certain terms in this nonlinear coupling seriously, which are coming from the density fluctuations. And this is what gave rise to the mode coupling theory, and first started due to Bushman Goetz actually from Munich and his group. And then we also were involved, Sriram, me, G, under in his group, and then all that. So that's a long development, but let me just very briefly indicate what is it. And before I go into that, there are two kinds of relaxation that comes in glassy system. I'll come to the MCT in a minute. One is, power law relaxation. By this I mean that this alpha here means there are different kind of relaxation in glassy system. There's alpha relaxation, beta relaxation, long time relaxation, short time relaxations. The long time relaxation can have a power law growth. That means as you are lowering the temperature or increasing the density, the relaxation time is increasing. By relaxation time, I mean you create a fluctuation in the system, and the time it takes to decay that fluctuation and come back to equilibrium. So again, we are talking about still equilibrium systems, though one can argue real glasses are not equilibrium system, but let us say we are considering dense fluids. Because the whole idea of my talk today here is, and all my work is that we are trying to understand this from the liquid side. There are many theories of glasses. One can look at, first assume it as glass, and then do a theory of glasses. There are material physicists and those, they are working on glass models like that. What we are trying to do is from the fluid side, if you try to access how you reach the freezing. freezing means freezing on an amorphous solid. And in these, as the relaxation grows, there are two kinds of relaxation growth. One is this power law relaxation. As you know, power law relaxation only increases very fast when you get very close to the transition. The other is this kind of thing which we call Vogelfulcher, that is around some T naught. As T goes to T naught, this thing shows very phenomenal growth.
They are different.
Which one? Yeah. So this happens over a different temperature range. This happens over a much lower temperature range. Let me go there. So one of the classic plots that we keep showing in this is this what is called the angel plot. So what he did is he plotted the relaxation time over some microscopic time scales, and you can see the relaxation time goes over 16 orders of magnitude. And he plotted different material. Now he plotted for each system, there is a characteristic temperature TG that the experimentalists use. What they call TG is when the time scale of relaxation reaches around about 100 seconds. So 100 seconds is on the time scale of the laboratory. That means if it goes even much farther than that, you cannot keep waiting for the system to equilibrate. And that's when they say that some glass transition has occurred. This is an experimental way of looking at it. So for every material, there is a temperature like that. So divided it by that and plotted it. So by definition, and this temperature is defined when it reaches 100 seconds or this kind of viscosity. So all these curves will meet at this point by definition, by your choice. But then what you see is that it shows this point doesn't have to be a single point, but different materials, some materials show a straight increase and some materials show a more. First, they show an increase like this, and then they show a very sharp increase with a very short temperature range. So suddenly, the fluid freezes. The viscosity increases by 14 orders of magnitude within this temperature range for those materials. These were called fragile glasses, whereas these were called strong glasses. The way he classified it, he measured the slope. I think I messed up. He measured the slope of this curve at this point, and that was called the fragility. And as the fragility is higher, you call it more fragile. And this is strong liquids. Silicon glass, the window glass, and these are more like strong glasses, whereas these are like Salol, OTP, orthotarphenyl, and all this sort of stuff. So there are different kinds of relaxation in this system. And my main point of showing this is to indicate that there are two types of relaxation. And this was shown more clearly in this plot by Ernst Rosler in 2006. What they did is they defined a new variable, which is m times t by tt minus 1. M is the fragility. So if t goes close to tg, then this variable z is equal to this, becomes very small. So on this plot, where you plot z times k naught, z small means you are at very low temperature. That means you are very close to Tg. And as this becomes large, then you go to larger temperature and you move away from this. Now, what they showed that, and these are relaxation time data for this many glassy system, that till some high temperature, the relaxation is very much like a Vogelfulcher type. Because if it is Vogelfulcher, then it will be a straight line because it will follow this kind of form. And here they plotted the tau, the actual tau versus the corresponding Vogelfulcher fit. You can see that up to this Z value, the fit is very well. That means the relaxation is Vogelfulcher. But at higher temperatures, you start seeing this kind of power law relaxation. And the general terminology that has developed from this is that these sort of relaxation are more characteristics of the mode coupling movements that people have studied from microscopic. These are things where barrier starts building, that the system has to overcome barrier to form class. So, and this is the last part that I will talk. But let me first come back to the little bit to the MCT. Yeah.
You were talking about this relaxation. You said that if I start a little perturbation, how does it relax?
Right.
Now, if I now think in terms of those conservative, those propagating sound modes,
yeah,
which you mentioned. So I can think of them, okay, these are propagating as well as widening. The
No. Yeah, I know what you mean. Uh, when you are thinking in terms of the sound modes, there are two things happening. One is propagating, the other is that the sound mode is getting damped.
Yes.
Okay. You are sitting there, if you are sitting at the gate, you will not hear, it will get confused. This damping is related to the viscosity. And that is the relaxation time of viscosity. So that as the viscosity gets very large, the relaxation becomes very, very long-lived. Whereas the propagation is the speed of sound. That would be there even if there is no viscosity in the fluid. So in the gas or everywhere you see that process. So there are two things when you are thinking in terms of that. So in all these equations, when MCT show the equation, you see that there are two parts to it. One is the propagating part, the other is the damping part or the frictional part or the irreversible part. It is the irreversible part where transport comes in. And glass transition is something which is very uniquely, the density is not increasing much, but the viscosity is increasing by 14 orders of magnitude. So that's the thing that one has to look at, that what is the mechanism that grows the relaxation time to such large value, though the density has not increased much. Though I should say that we really don't still know that what exactly the microscopic way of doing. There are different forms of the theories, different things you can do, but not exactly from a very microscopic theory telling that, okay, this is what is called, like the way we understand critical phenomena. You know, like the renormation group, you can do renormation group, you can see the scaling and all that. That kind of understanding has not been there.
It is not possible to identify which of these two relaxations that you mentioned.
Yeah. The other is not relaxation. The other is not relaxation. The other is a propagation. That's it.
No. These two, the VFT and the
Yeah.
propagation just comes from linear
Right,
height analysis.
yeah,
You don't
yeah.
even have to go to non-linear
Right.
terms.
Yeah.
But the dampening or dissipation,
Yeah.
is it possible to identify which one is power law, another is exponential that you mentioned? Which of these two would actually correspond to dampening of these propagating modes?
That you do by fitting data. That's what I'm trying to say.
That's
When
it.
they do the fitting of the data, then they find that over certain temperature range, it is the
Okay.
exponential relaxation, which is, and you can see that from the exponential form, it's like barrier hopping. So some barrier has built up in the system, and at low temperature that is happening. At high temperature, where you can think of a continuous kind of fluid, they are looking at nonlinear effects, the mode coupling and all that has given rise to this power law, and that fits well in this higher temperature.
So if the sound mode is not important, probably you can get rid of from the beginning. Or is it possible?
So sound mode is
No.
sound mode is what is dissipated.
What do you mean by
sound
getting
mode is not
rid of?
dissipating. That's a different mode. Sound mode is not dissipating.
No, sound mode is dissipated. Sound
No.
mode is propagating.
No.
That
Its dissipation is proportional to the viscosity. But what do you mean by getting rid of?
No, getting rid, we start with the equation where there is no first derivative sort of thing.
Yeah, you can do that. You could have done that.
Or also Galilean transform. So
No, not Galilean. You can do an overdamped transformation. You can write down models which you call Dean-Kawasaki equations, and you can get models where you can look at only the transport part. And there you actually don't look at the viscosity. You look at the diffusion constant. The diffusion constant goes to zero. Self-diffusion constant. Think of that. So it is some transport process, but you can get rid of the sound modes at the beginning and do that. Okay. So one of the things that happens in this Vogel-Falcher form or the exponential relaxation is there is a thing called configuration and entropy crisis in the glass formation. That means there is a particular property of this system which is related to configuration, and this was originally started from this thing called Hausman paradox, which I think in today's context people don't take much weight. I've seen sometimes referees getting very upset for even taking Hausman paradox name. But the whole point is that he first talked about this idea of configurational entropy, which he defined as the entropy of the whole system, the supercooled liquid, which you still assume to be in a metastable state. Otherwise, you can't say that there is entropy. And then you subtract from it the vibrational part of it. So think of the fluid as already occurred some kind of localization, and you look at the vibrational modes, and extract out the vibration part. He had different ways of calculating it. I am not going into it, but it is the difference that he calculated, and he showed that for the fluid state, at some point it becomes less than that for the crystal state. So that means the crystal has less entropy, more entropy than the fluid, which would be because the fluid is disordered state, which will be an absurd thing. So there is this issue that there is a point beyond which you cannot continue the fluid state. So he resoluted it, saying that it could be most probably crystallization will occur, or one can think of some ideal transition will occur. Today, that is not so much of a matter of discussion in glass, I think, but what is of more discussion is there a phase transition at some point down the line, or how does this rapid fall off of configuration entropy occurs? So that is a thing. New models have emerged. I'll discuss towards the very end. That's the work I did with Prakash. And these quantities are called complexity, the configuration entropy. In what context it is called complexity? You discuss in terms of free energy landscape, and then you take the log of that to call it the complexity. So the complexity is like a theorist definition of configuration entropy, you can say.
We have another 25 minutes left.
Okay. 25 minutes. Right? So that gives rise to this thing, what is called the landscape paradigm. That means if you discuss the physics in terms of complexity in the free energy landscape, you discuss in terms of landscape. So far, if you just pay attention to the broad outlines, I have talked about continuum models, density functional theory, and then this kind of hydrodynamic models where you look at slow modes and all that. But this is a different way of doing things. You look at the landscape of the system. Now, the idea of landscape originally came from potential energy landscape, where you look at the mechanical energy of the system, look at the potential energy landscape. And this started, I think, mainly with Stillinger, and Srikant was also involved, Srikant Sastry in the initial stages, and he has done a lot of work on that. So the name comes from more there, that it is the landscape of some potential, and think of the system moving in that potential energy. Like we know this, if we take a single particle motion, if it is moving in some potential well, it is moving in that well. So that's the landscape, like a one-dimensional picture. Think of this a multi-dimensional generalization of it, which was first, I think, proposed by someone named Goldstein, the Journal of Chemical Physics paper in the 60s. And then Stillinger and others, Devendra Sastry, those people developed it for glasses more. And that approach has sometimes been used also, similar approach, for in terms of not the potential energy landscape, but the free energy landscape. So instead of a single free energy, you think of the landscape, and if you can think of that, even the density functional theory, what it is telling it is that you are in the local minima or the crystalline minima or the liquid minima of the free energy landscape of the fluid. So one can look at metastable landscape and then calculate the number of minima of such on the landscape that is occurring, number of metastable minima, and treat that as a configuration entropy. Because if you have many such minima, you have many such configurational structures where the system can go, and you can have glassy structures. So that is, this kind of definition was more used by Parisi and others who were doing it in the spin glass context. So in this landscape paradigm, what I mean by landscape, what I mean is that suppose you take the Gaussian approximation that I mentioned earlier, and now these RIs, which are the centers of this Gaussian, you start treating them as parameters. So you'll have a multidimensional space of landscape where you can calculate different values of rho and different values of a free energy functional, for example, Ramakrishna Yusuf, and then look at the corresponding minimum of that. This kind of studies have been done by someone was asking the alpha values for different alpha by Chandan, Ajay Shuz and others. There's a 2008 PRL for glassy structures. So the free energy landscape, the key idea in this, that the theoretical calculation that I'll mention not the simulation thing, that the free energy landscape kind of fragments. Think of the free energy landscape as a single minima in the liquid state. And then as you cool the system, at some point, this free energy landscape fragments into many, many minima. And it is, by many, many, many minima, I mean exponential in the number of particles. Because if you take the log of it, the entropy would be proportional to n. That means it's e to the power n. So in that situation, when you have the landscape splitting into many, many minima, there is a way to calculate the free energy. So I'll briefly mention that. And there you use the replica method. So that's another method of calculating free energy.
Is there a way to say from have kind of things like that?
If I have it,
Hamiltonian or some microscope model or some model.
Yeah.
Is there a way or some prerequisite that you can check to conclude that this can have an exponentially large number of minima?
not a priori that I know that if you give an Hamilton one, people, that's where people check. With simulation, with this potential energy landscape study, that's what people have studied. At least look at the mechanical minima and count it, how many minima there, and in a lot of these structures, they have seen that if they count the number of minima, because you are doing in a finite system, and you see this configuration entropy forming. But there is no general sort of thing that, okay, if you give me the minima, I can do this calculation and show that, okay, there is this thing. Something I like that I'll explain, but that's a different sort of. So just to briefly that there are two kind of studies, dynamic and thermodynamic. The dynamic is this ergodicity breaking transitions and all that, the glass transition or the mode coupling transition, which I'll spend next 5 minutes or so on. And then we'll discuss the study of the free energy. That is the thermodynamic approach, or the way to calculate the partition function using a replica trick.
And one more question would be like, how do you guarantee that changing the answer slightly of your density function?
How do I guarantee?
How does one guarantee that if you change your answers for your density function?
Yeah.
Will not increase or decrease the number?
No, there is no guarantee in this thing. You can even say that how do you know that the minima is suppose you check for FCC, there is a minima. For BCC there is a minima, but it is higher than for FCC. So you say, okay, it will be FCC, but you do not get the spontaneous breakdown of the symmetry from the theory. You assume it and then you check it. That's the idea of this kind of model. Now, that's what you get, but at least if you have a quantitative control, that given a structure, you can check whether this will be a minima and all. So that but yes, it is not something where you can say a priori that, okay, this will cause.
So this configuration entropy, can it be then treated or cannot? Can it not be treated as a thermodynamic?
It is the thermal. That's what it is treated. We'll try to calculate it
So
from
that would kind of imply that it should be answered independently.
Yeah, and we will try to calculate it from the partition function. So it has. Okay, so coming back to the question that she was asking at the beginning, that, and also you wanted to know. So these are the general structure of this mode cup, the hydrodynamic, nonlinear hydrodynamic equations. That you have the density satisfying this is a little different from the equation that I was seeing in your office just now. There's no dissipation in the density equation at the simplest level. So this is a completely reversible equation, continuity equation, and then you take the momentum equation. There's a pressure term, and then this is the usual viscosity term that is causing the damping, and then there is this term which we call the Navier-Stokes nonlinearity, or the Galilean invariance term and all that. What happens in mode coupling, what one takes seriously, is that the pressure is proportional to the density and then the higher powers of density. It is those coupling that corrects the basic theory, and you get the correction to these transport coefficients. Okay. Now you can always simplify this equation by combining this, so that these terms sort of become, this doesn't become absent, but this gets transformed into a diffusion kind of equation. And so you will not have this kind of propagating sound modes in that, but you will get the diffusion equation. But then you can look at the renormalization of the diffusion equation and then get the similar kind of model. But there, whereas in this full theory, you will see the LIG, these viscosity corrections are diverging. There you will see the reverse. The diffusion constant actually goes to 0. But that comes out of the theory in a natural way. Okay, so that's the basic philosophy in doing this, that you calculate these effects of those nonlinearities in this equation. Yeah, and non-local. The reason it is non-local is I've written it like this, but you should realize that it is like, if there is a density nonlinearity, it's not delta rho x at the same point. It's delta rho x times delta rho x prime and then integration and all that. So density fluctuations at two different points are getting related and related through some coupling, which is the structure. So the non-local part comes from there. So in this way, we say that it's non-local and non-linear effects that you bring in this thing. But all these are done for the continuous liquid kind of state, that you have a liquid and then you are making an expansion around a uniform density and all that, and then doing the lowest order one loop theory. So the order parameter in those things become the product of two density fluctuations. So generally you will take the simple density, like in density function theory, this is the order parameter, the rho itself. But now you take the product of it, and then if you calculate the average of it or take the long time limit, that's the long time limit of the density correlation function, time correlation function that I defined at the very beginning. That quantity jumps from a 0 to non-zero value. If it is an ergodic system, then you can think of this as splitting up, and then it goes to 0. When this jumps to a non-zero value, you say that there is a transition in the theory. This is what is called the MCT transition and all that. And it's a transition which is virtual, because as the system gets more dense, it doesn't support the transition. But at least at the initial stage, it shows very, 3-4 orders of increase in viscosity in the system, which is all you are looking for at that temperature range. And again, this pressure comes from this sort of term in the Langevin equations, if you are a little familiar with fluctuating hydrodynamics. But the key point of all this is this quantity, if I call it F, the long time limit of this. This is like an order parameter of the theory, and you get an equation for a nonlinear equation for this order parameter in this kind of form, from the corrections and all that. And when you solve this equation, this nonlinear equation for the order parameter, you see that there is a point beyond which all the non-zero FQs are supported. But if you are below that density, then you have the non-zero densities are not, non-zero FQs are not supported. So this was called as an ideal MCT transition. People initially was excited, and then it was shown that the transition really doesn't occur. And so, but in the initial stage, it shows this growth. And then particularly Goetz made a lot of comparison with experimental data over shorter time scale, shorter length scale, and it showed good agreement. And that's where MCT has this appeal. If I will remember more to this article on this, you can look at it. There's a lot of physics that came out of it, but not the final glass formation.
The previous slide,
Yeah.
when you put this T goes to infinity limit,
Yeah.
for the ordered phase, you said it's going to be non-zero.
Yeah.
But that means that it's really not T goes to infinity, that T goes to tau, that relaxes, which
No.
is very large, but
That tau goes to infinity.
tau,
T goes to tau, not T goes to tau. Tau is the time over which it is decaying, right?
Yeah.
So it is saying that as
tau diverges,
if this does not, this does not decay to 0, that means tau has gone to infinity. So if you have a correlation function, think of this. It's here. It's more like this. You plot it with time. I don't have the curve. Why? Yeah. So you see, it would have gone like parallel to the x-axis forever if it was an ideal transition. But what more, and I have actually done a lot of it myself. that it actually decays out. I'm not going into all that, but these are things which we cannot go into. So the ideal transition would mean that this will remain parallel to it and you will go to infinity for all time. So for initial states, these were a good model, and people still keep using it. People are using it. Even last week, I saw a paper for active matter. People are using this kind of coupling model. See, basically equations of hydrodynamics. Then you have nonlinearities. So you can look at the effects of the nonlinearities and construct models like this. So this has actually given rise a lots of studies for relaxation in condensed matter systems using this. And even there are theories of localization and all this, which initially Goetze, who first started all this, they tried to understand Anderson localization using this. There are papers, many papers on those lines also. And this is the f of q solved, and this is the time scale. And if you look at the r square, how it is growing. So if it is constant like this, then that means the fluid, the particle is completely localized. R square is no longer growing. But of course, it keeps growing. It's not completely localized. But if it was like this, that would be the ideal transition. So over a time scale, the plateau holds. Over a time scale, the plateau holds, and the localization occurs. And this is where the simple MCT people have made appeal to. These sort of model, because this was showing earlier transition, Jean and I looked at it, and this is a different set of paper. 2009 paper is different, but 2012-13, we took a different approach to it, and the basic approach, I'll just take 2 minutes to say it because it's fine. Instead of doing this kind of slow modes that I was telling you, there what was done was you start with the microscopic equation and do a field theory of that. So you start your Martin-Cigliaro's action and all that, it becomes, you do not take the hydrodynamic equation. That means you do not take this thing I said, a set of slow modes, and then form a field theory of that. You take the microscopic equation and then you do a field theory of that. If you do that, then your basic theory doesn't even have any interaction. So the basic theory is the non-interacting fluid, and then you have the theory in terms of the interaction. So in the earlier case, what people have generally done is that people have looked at those hydrodynamic equation and looked at how the coupling of the hydrodynamic modes will affect. Here what we did is we looked at the non-interacting plus the interacting theory. So you can do that using methods of statistical mechanics. It's quite involved. If you are interested, there are 2 very long papers in statistical physics in 2013. You can look at it. And what has happened is this theory is not just for glasses. This has found a lot of application now. I see more citation of the paper from astrophysicists because they can study this. They call it kinetic field theory. That means you have a set of particles, and these particles are evolving in time, and then the correlations of these, how the correlation develops and all that. That even for a non-interacting system, one can do that. So these kind of models are useful even for studying other condensed matter systems. And the idea again is that either you take a Newtonian system or a Brownian system. Newtonian system I actually did with him. Then Brownian system he had already done. So you can take either systems and calculate it, the action, and you can calculate similar MCTs and all that. What happens is, I'll just tell the main key upshot of the result. In the earlier case, this transition was occurring too earlier. It was occurring at too low packing, which is not very physical. Here we could show that when you order it in terms of the interaction in the system, then the ideal transition, which is virtual transition, shifts actually to very high packing, about 0.62. And this was a key thing that came out of that analysis.
So what are the X and Y?
Huh?
X and Y.
Yeah. So this is again the that non-ergodicity parameter I was showing you, but now done for this theory. The only thing that changes in the theory, the vertex function in the theory gets changed because you have organized it in terms of the interaction in the theory. And so then you look at the effect of interaction. So you have the basic theory, which is non-interacting, and the interaction. And then when you model it that way, then you see this non-zero solution to those parameters, FQs, this thing, this equation. So what has changed is this vertex function. So the non-zero solution to this occurs at much higher density, and that was the new thing that came. Let me now move on to what I quickly do what I did with Prakash. So basically, the density function theory and all this, you can think of these also in terms of continuum models. Like you can think of the density as being averaged with some average, some kind of a coarse-graining function, and you can write down the free energy of the system e to the power minus beta f by taking trace of this over the statistical mechanical ensemble, and you will get the free energy in terms of the fields, so rho and g, and the rho part has the entropic contribution of that. When you calculate it this way, there is a nice paper by Langer, Jim Langer. They were doing this, of course, for the fluid transition, fluid to liquid to gas transition, but you can write down similar models, similar to what TVR and all those people wrote for the free energy in terms of a continuum field, n of x or rho of x, whatever you call it. And it has an entropic contribution, and then it has the interaction contribution. So this is the ideal gas contribution or the entropic contribution, which is typical. And this part you can calculate exactly, and then the entropic part you can, the energy part you can write in terms of interactions, which is the free energy functional and all that. Now, this has been used for crystallization transition. What we did, and taking a clue from some other earlier works of Kirkpatrick and Thirumalai, that one can use a replica approach to calculate the configuration entropy and these sort of properties for the glassy state. And that I'll discuss. What, 10 minutes?
5 minutes in principle.
Okay,
But there
I'll
are
take 5 minutes.
a lot of questions, so 7 minutes.
So in this, and this is the work that Prakash and I did. This is in physical review this year. There's another paper in Journal of Non-Crystalline Solids. So this started with the idea of first there was this paper of Journal of Physics A. It's less of his more famous papers. This came out in Journal of Physics A, the mathematical. But it is, when I talked to him, he says it is one of his most favorite papers. But it got less attention, I would say. So what he did is, in terms of the density, he tried to calculate the partition function. So you break it in terms of this free energy landscape splitting. Because you have minimized the free energy landscape. So you put this delta function constraint, that you have e to the power beta f, that this is a, if this is a minima, this will have this thing. This b is beta, sorry. This is error. But basically it's the functional derivative of the free energy should be 0, this is a local minima, and then we calculated it. Whereas we got some progress, but it was not exactly completed. It was actually completed in a classic paper by Remy Monassan. This paper is one of the it's classic paper, I'd say, in class physics. This is a 1995 paper. You can look at it. It's quite good. Here he gave that idea, followed on that work of Patrick and Thirumalai, I would say. It's referred in his paper, in this PRL also, that he calculated by putting an extra field in this, phi of x. And he puts this field phi of x, and it's like it picks up the minima. So if phi x is equal to psi x is the phi and psi. So psi x is the field he introduced for picking it up. Phi x is the general field, like density or whatever you take as the order parameter field. And if it is 0, then it shows a minima. So he writes this thing in this way. Then he calculates the free energy for a beta, which is equal to m times beta. And you take m as an integer. What happens is, it's quite nice trick. You can do the integration through a Hubbard-Stratonovich kind of transformation, and write the free energy for the system with temperature V time in a form like this. Now, here he used the idea that, well, I can calculate this. See, this has this part, and then there's a coupling part. But I can calculate this as a composite system where I have m replicas of the ideal system, original system. So I have the original system, and then if I generate m replicas of the original system, that composite system's free energy I can calculate. So he calculates that free energy and all that, and then takes the limit m going to 1. So this is quite different from Paris's original idea of replicas, where it was calculated for m going, if you remember, n going to 0, because he needed to calculate log z average, and he took this n log z e to the power this and n going to. But this is not that. This is quite physical. You take at the end n going to 1 limit, but by looking at this composite space and looking at derivatives of it, you can calculate the number of such minima and all that. You can have the formulations like this. This was used by there's a number of paper by Peter Mullines and others where they can use this method to study stride classes and all that. But no one so far had used the density functional form Hamiltonian to do this kind of calculation. And that's what Prakash did in the thesis. So you have basically order parameters now defined as two kind of order parameters: density fluctuation. So we are taking the continuum field as density field, and you have two kind of order parameter. One is the coupling of the density fluctuations in the same replica, and coupling of the density fluctuation in the two replicas. Now, if it is in the same replica, it is density fluctuation in the same replica, so it will be the structure factor. But if it is in the two different replica, this is what was cited as the order parameter of the glass transition. That if that is non-zero, that means if there is inter-replica correlation developing, then you say that there is a glass transition or a.
No, these replicas can I think of a system at different temperatures?
No, they're not the system at same temperature, identical copies.
Okay.
If they start, so you can think of they are locating the system in different, the system in port in different minima. So if it is so long-lived that a correlation develops, you say that
between two minima or something.
two minima, and if that happens, then you say there is an ideal breakdown of symmetry.
What happens if this also replica symmetry?
I'll come to this. Let me first meet this time limit.
Sure.
So you have two kind of order parameter. One is GAB, which is inter-replica. This becomes the order parameter. What is interesting is that what we found when you did the calculation, that this order parameter, so these are the general structure of this Dyson-Swinger type equations, and then you look at the minima and all that, look at the implications. But you see, this equation that you get for this new order parameter is very similar to the equation that you get for the mode coupling transition order parameter, that you have a vertex function and all that. Only difference is that here the vertex function has its free contribution coming from the three particle correlation. There's a multi-particle correlation in the system instead of just two particle correlation. At the two particle level, there is no effect at this nonlinearity. It's at the three particle level it gives rise to it. So what he needed to do is he calculated the 3-point correlation functions for a normal fluid and then used that to calculate the entropy and all that. When we did that, so these are the vertex function that he needed to calculate, the 3-point functions and all that. This is the 3-point correlation function he used, calculated using the Barat method. Barat had a method better than superposition approximation for liquid structure. So using that, he can calculate again the order parameter, and you can see the order parameter is one restriction in this, that because of the size of the particles, you have a upper cutoff in this sort of model that you use. Otherwise, it will show divergence. And then we can calculate the configuration entropy. And as we go to lower densities, you see that we do not. You can push it to higher density, I think, flat off, because the structure is not even trustable at this density. But at this density range, you start seeing this kind of fall in the configuration entropy. And then from that, you could estimate the point where the extrapolated configuration entropy will go to 0. This is the point that I was mentioning, Kauzmann point or Kauzmann paradox. So one can estimate those things, and these are pretty much in agreement in the same range that you people find by doing simulations or other calculations. So this is now reported if you are interested in more detail. This, but basically these are coming from the multi-particle correlations developing in the system. The 3-point this kind of correlation, that this contribution, that this equation that we are solving, because you have to have the non-zero f to get this configuration entropy or complexity. So this quantity is only non-zero beyond a certain density, and then the key contribution comes from this 3-particle correlation in the system. So yeah, I'm sort of out of my time. So let me just, yeah. So this is another thing that we use this kind of structures to solve these models, and then you see there's a change in the way the configuration entropy falls. It sort of shows a more linear kind of fall. That's a difference. If we use a density functional kind of model to estimate the structure. Remember again here the structure goes as an input in both theories. So this is just a summary of the last part that I said, that the classical density functional approach to this thing gives rise to local free energy minima. And then we use this continuum field theoretic model for identification of the free energy landscape fragmentation and the MCT transition. By this I mean the similar form of the equations. And then we calculated using the structure, the configuration entropy. So I just try to briefly touch this. If you are interested in this kind of approach, I would say that look at Remy Monassen's paper first, which was starting of all this. And then there are a few works like this. I don't think this has been looked into much. That method. Parisi also did. Parisi, there's a paper by Parisi and Measured where he calculated for low temperature glass using this sort of thing. But the first contribution in this, I think, came from Kirkpatrick, and after that, the Monassen paper. The Monassen paper was a key breakthrough. Okay, thanks for your attention. Yeah, someone had a question.
Yeah, so I was just curious what happens if you said only correlations develop that can be considered.
That's defined as the
that defines it.
Yeah.
So can the replica symmetry break? Can order parameter symmetry break?
No. The replica symmetry breaking, that term you are using, this is using the spin glass. Right. But here we are not talking about any kind of replica symmetry like that. So it is the term that is similar, but that in the sense that you are using the identical form of the system to calculate the partition function. I think beyond that it separates. There is no replica symmetry breaking in this.
But the symmetry is there. Replica symmetry is there to begin with.
Replica symmetry here is assumed, because if you have identical system, then you take a system with identical replicas and call it different replica. Now you can say that when you have this correlation developing, you call that as replica symmetry breaking. You can call that, but I would say that that is just borrowing a term from the spin glass terminology, because it can create, using these terms as a problem. This happens a lot with the DFT. I have seen this, especially in the context that different people use the same term for the same thing, a different thing, then it becomes very complex. So I don't want to call it replica symmetry breaking. I'm calling it spontaneous ergodicity breaking, because this means that there is a situation where the landscape has fragmented into many minima, and then you have some kind of a correlation.
So you're talking about this C3 correlation, right? Three-particle correlation.
Yeah, it's actually, I didn't get the. It's a 3-particle correlation, but it's the 3-particle direct correlation. Yeah, so it's the higher brother of Einstein's. You know, I know you know this, but you know people may not know this. Yeah.
So what I'm asking.
Yeah.
Free-body correlation comes with essentially like saying the caging effect, etc. Like because we know in glass there's the caging of the particle.
Yeah.
So that gives rise to higher order correlation.
Yeah.
Now, what is the experimental significance of C3? As far as I know that C3
what is that?
Experimentally,
Yeah.
can it come in C3? And do you know any measurement that can tell about C3? As far as I'm aware, I don't.
That question you can ask for fluids also, right?
Yeah, that's the thing. Yes.
Yeah.
Even for fluids, not most, right?
I don't know. You mean
Experimentally, there is no method which can actually determine C3. That's the problem, major problem, right?
true, but one can use, you know, like similar things like Ornstein-Zernicke. And then I don't know that this was in the statics of fluids area people have looked at it, but one can look into modified forms of Ornstein-Zernicke related to the 3-point pair function.
No, I'm talking about the experimental determination.
Yeah, experimental also I'm saying that experimentally there, I mean, experimentally you mean neutron scattering and all this sort
Yeah,
of thing.
kind of neutron scattering or something.
But one thing
I'm not
I,
aware of anything of,
yeah, so I think they have to calculate somehow higher order correlation functions, pair correlation.
it becomes model dependent. Right?
Yeah.
The C3
Yeah.
Model.
So this become model dependent.
Okay.
And I think another problem there is, I'll tell you, as you were saying, it sort of strike me. You see, it's the pair correlation function that is related to the neutron scattering factor. And the reason is it's a two-body interaction.
Absolutely.
So and generally in condensed matter thing, you always do two-body.
Yeah.
But if you go to, and we don't consider, but 3-point would go into that. But I would say that there could be cumulative effects or corrections of these things calculated in terms of higher order correlation and then looked into. Because it is there, very much there in high density.
Yeah.
Sure.
But well, experimental signature is
Simulation can easily do it.
Sure. Yes.
Simulation can
Yes.
easily do it.
Any more questions?
I have a question. You have talked about the free energy landscape, which are very minimal. We talk about what about the large deviation function of them.
What is that?
Large deviation function.
What?
They have free energy, which are very minimal.
I am not sure what you are meaning by, first of all, let me say this, large deviation function. Do you mean that is extreme limits?
So I think maybe let me reframe. What
Yeah.
you for one minimum, you
Yeah.
calculate a free energy.
Yeah.
Other minimum, you calculate free energy, get different value. What is that distribution? Or rather, yeah.
Well, see, the idea is that there is but for a particular free energy value, you will have a set of minima, and you are talking about so many minima and all that. Now, as you go back to lower values of free energy, the number will change. But there's a cutoff beyond which it will not go. The liquid state value or something. And this cutoff keeps moving. But you have to realize that all these functions are not known exactly in any mathematical form. These are all qualitative descriptions. The only thing that I have seen is Monassan work, where he could make a kind of field theory to just enumerate the number of such minima. But beyond that, all the images you see and all that, either it is for potential energy landscape, that even you cannot plot, right? It's just a n-dimensional space. But actually you can get the number. In the free energy landscape, we are talking in thermodynamic limits. So I do not think that there are exact numbers you can say that it is this value or that value. So the expectation is that from the physical consideration that it will remain within certain bounds, and then there would be minima at a certain value, and then from that you can calculate the configuration. But these are qualitative. I don't think there's quantitative values of this that you can make precise mathematical statements.
Just to add, I know why he's asking this question. So I think, do you know any literature where people have calculated, like he has recently read one old paper by Derrida, random energy modulation. So do you know that people have calculated such things? No, I mean, maybe this is
Generally, these models you see either they are doing it for some specific computer model that they can calculate. But calculating it in the thermodynamic limit, how many free energy minima, that this is only this sort of thing I have seen. That where you use a field theory to enumerate the numbers and then look at it. Beyond that, whether, I mean, first of all, the fact that it breaks into such minima is an assumption. The whole calculation is based on that assumption that it, beyond a certain point, it breaks into, so suddenly the free energy landscape. Think of the free energy landscape of the liquid state. So you have one minimum, uniform state. And then as you cool the system at low, this landscape fragments into many minima, the system gets trapped. Now, I don't think there's even a clear theory that it shows that it happens this way. That's an assumption. Based on that assumption, you calculate the partition.
Computer you
can do it in the landscape, but I'm saying in the analytical calculation, you really don't see it. You assume that, and then you calculate the partition function by dividing the whole partition function sum in terms of this landscape, these basins, and then you add them to count the number of.
Okay, no.
You should also ask online. There are many people learning online.
Okay.
So one thing is,
This was online.
yeah, many people are learning. So in the case when you are just supposing the mode coupling theory, we neglect all higher order couplings beyond the quadratic level.
That's,
When we say nonlinear,
no, that's not a very correct way of saying. The correct way of saying it is you ignore all corrections beyond the one loop level. Where's the pen? Yeah. So,
I think maybe you can draw the
when you do the MCT, you get corrections to the viscosity with diagrams like so. So this is a density correlation. This is a density correlation. So you can get higher loop diagrams. So you ignore the higher loop diagrams, but not beyond the quadratic, because you can dress in some of those into this kind of one loop diagram.
but in the features which you develop from the microscopics, that's what I was thinking. What is your small?
There you start from the equations, microscopic equation, then you get the coarse-grained equations. Okay, here you don't make any approximation on where you cut off, truncate the thing. Here the approximation you have to do some kind of coarse-graining, because think of a Newtonian system, the dynamics is completely reversible. But when you write down those equations, they are irreversible equations. So you have to put in the irreversibility by hand. If it is Brownian dynamics, you will get it. But it is all this kind of approximation. But then you get a model where you have higher order nonlinearities. Now the thing is, how do you calculate its effect on the transport coefficient? There you do this kind of. In principle, one would say that you should do it higher order and all that. I mean, we have tried doing even solving those equations, not even going into this. Solving these equations, I have papers with Jalvi Barat, these people, where we solve those equations in the computer, like Chandan also did earlier. And we see similar things, but there again, there are different kind of numerical problems. But you don't do any one loop at all.
If you take the ladder of this loop, right? I mean,
in this sort of thing, you can take some of the, but the ladder will only consider a certain class of.
Yeah. But when you make good calculations, then first of all, you are assuming that the field theoretic proposition that it is partiality.
Yes,
So
yes.
you're assuming it is
Partiality.
And now, what I understood that
That partiality behavior becomes large.
yeah, the maximum contribution to the path integral will come from those minima, from the saddle point approximation, and then you are making these loop corrections.
No. You're mixing the minima thing is in the DFT or the free energy calculation. But what you are saying basically is a key problem in this kind of model. That is, you have an effect which is becoming large, and you are doing a, so there should be the problem with, and you do this sort of thing. This is stated even in 1984 paper when we wrote that, and the term we use, it is even sobering that you are cutting off the theory, which is you need to use dynamic renovation group and things like that, but it is difficult to do it in this kind of thing because you do not have any reason to use dynamic renovation. There is no self-similarity in this sort of system. If you are doing critical phenomena or turbulence and things like that, there Boston is Stephen, you can do that sort of thing. So that's a problem in glass problem. That's a sort of handicap in there. So one has to use it, but nevertheless, people have used this. As I said, the transition also is not doesn't survive. There are certain nonlinearities in the theory which finally cuts off the transition. And these are theories I have done a lot. Even right now, there's a paper in physical limit consideration on this. But these are more technical things. There's no use talking in colloquium about that. If you are interested, I can tell you about that.
So you have shown that the viscosity term that one can calculate order parameter by order parameter. This is quite large in the glassy state, and that is also related to the relaxation of the power, relaxation of the fluctuation.
Yeah. So the viscosity divergence is power law, and so the relaxation time also diverges power law.
So I'm asking that is it quite large or it is a divergence? That is a divergence point, something like that.
Yeah. So it has not diverged yet, but it is if you fit the theoretical prediction, it will fit a power law as if it is going to diverge. But before it gets there, other effects come in so that it smooths off. That's the thing. Like if I show you. See, in this, it's sort of like it fits power law here. And people, there are, if you find in literature, there are angel plots shown in that way also. It shows a curve going straight up like this. So the divergence point is around here. But before it followed that track, it crosses into a different kind of relaxation.
So this is the main difference from the glassy state from more compact solid state. Right? The divergence, viscosity actually has a certain. If we talk about the viscosity in the solid state, that should be diverging one day also. So,
not necessarily. You can think of the viscosity around the solid state. You know that what is the sound attenuation? So in a glass, sound mode is there. You can look at the sound attenuation of that, but that is different. That is after it, assuming that it is in a non-ergodic state, then the sound, how the sound is propagating. Even in a crystal, you can I have actually papers with Kinetic where we calculated the elastic constant, the transport coefficient of the crystalline state. You can do that, but that assumes that you have already the crystalline state and then the sound attenuation about that. But in the glassy state, the point is that coming from the liquid side, the viscosity starts showing a trend of divergence. And before it diverges, whether it diverges or not, that is even not experimentally made sure, because before it diverges, relaxation time shoots up so much that you cannot wait to calculate the. This is the, and that's why when it crosses the laboratory time, then it is called glass time. I mean, someone once said that we do not even know why glasses are there. That is why the particles are getting frozen like this. But then it's a question very difficult to settle experimentally because you cannot wait to see how whether it will diverge or not. So one has to do it in an indirect way, extrapolation or theoretical predictions.
Any more questions? Okay, there might be some online questions and also comments posted. So maybe so the people online.
Not here.
Okay.
No question in chat box.
Oh, no question in chat box.
Rajesh sir,
No, why they can hear me? Right?
no one is here right now.
Okay,
Yeah.
so fine. Okay, so if there are no questions, so let us thank the speaker again.
Yes, ma'am.
Wrong link was circulated.